Okay, so today we talked about multiplying probabilities. So the other part of that is we're going to talk about when do we add probabilities. So some more vocab. A simple event is an event that consists of only one event. A compound event consists of two or more simple events. And so in multiplying, we talk about independent versus dependent events. Well, in adding, we talk about mutually exclusive events. So a mutually exclusive event are two events that cannot happen at the same time. So I'll kind of show you some examples of that, and then we'll talk about what happens if they can happen at the same time. So the probability of mutually exclusive events. So if two events, A and B, are mutually exclusive, so you have to know that word. That means they cannot happen at the same time. Then the probability that A or B occurs is the sum of their probability. So really, key idea is if it's A and B, you multiply. If it's A or B, then you're adding. And so you just take the probability of A plus the probability of B. So let's look at an example. So this is not a full deck of cards. Sylvia only has a stack of cards. She's misplaced a lot of them. She has 10 hearts, 8 spades, and 7 clubs. If she selects a card at random, what is the probability of selecting a heart or a club? And I really like writing it out. Like I like to say, okay, she's selecting the probability of selecting a heart, or, I'm going to write it that way for a minute, the probability of selecting a club. And I would draw that if I can, but I can't, so I'm going to write the words. So when I see the word or, I know I'm going to be adding those together. And so the probability of a heart. How many hearts are there? There are 10 hearts over how many total cards? 10 plus 8 plus 7 would be 25, right? And the probability of a club, this, I guess I should have said, this is mutually exclusive, because if she wants a heart or a club, she can't select both one card that's both a heart and a club at the same time. So that's why this is a mutually exclusive event. So there are 7 clubs out of 25. So notice she's only selecting one card, but I want the chance, is it a heart or a club? So that would be 17 out of 25. So again, you can leave that like this is a valid answer, but just like, again, sometimes people struggle with like, what is that? That is 0.68, which means there's a 68% chance, which should make sense because she's more than half the cards are a heart or a club. Huh? Okay. Do you want to do this one? Sure.
So a bag contains 3 red marbles, 4 blue marbles, and 3 marbles are drawn without replacement. Find the probability of each. So the probability of 3 marbles drawn, probability of each would be, hold on.
What is it?
So the probability of pulling 2 red marbles out of the 3. So what's the probability of pulling 1 red marble? Well, there's 7 total marbles, so it'd be a 3 out of 7. But be careful here. This isn't an addition problem. This is a multiplication problem because we want 2 red marbles, all right? And since we pulled them without replacement, then how many red marbles are left if we pull out 1? Well, we have 2 left out of a total of now 6 marbles. So we're multiplying these to find the probability of pulling 2 red marbles. Yeah. And if you put this as a percentage, it would end up being 11.4% chance of pulling 2 red marbles and 1 blue marble.
And so the big thing, nope, go back, we saw part B. The big thing that we have to think about here is you have to now think about, am I multiplying here, am I adding? And it's not always going to give you the word and or the word or. So now look at the next one. It says the probability of at least 2 marbles. So we already did 2 marbles up here, right? So the probability of 2 marbles is like saying 2 marbles, 2 red and 1 blue, right? That's the probability of 2 marbles. But what does this at least mean? Well, that means there could be more than 2 marbles, right? So that's like saying the probability of 2 red and 1 blue, or, which means plus, the probability, what if they were all 3 red? So that would be the probability of 3 red. And honestly, on this one, we don't really need to redo this one because this is exactly what you did up here. So I already know this one. I'm not going to redo it. I already know it's 4 over 35. But I do have to say what would be the probability of all 3 would be red. Well, again, there would be 3 red marbles to begin with out of 7. And then the next one being red would be 2 red marbles out of 6. And then there would only be 1 red marble left out of all 5. And that would be the probability of they were all 3 red. But if it says at least or at most, then you have to think about all the options there. And then this one would be 4 over 35 again, right?
6 over 20.
No, 1, 3 down here, right? It would be...
7 times.
I can't do math. Because I just simplified my 3 and my 6, and then I divided my 2's, which just leaves me with 1 out of 35. And the nice thing is that's a common denominator, right? That's just 5 out of 35. So changing it from at least 2 red, it really only increases it just a tiny little bit, right? Do that?
It's 1 over 7.
Well, yes, I meant the decimal.
Oh,
I don't know 1/7.
428 or 14.28%.
So about 14.3%. And again, I don't care if you leave it as a fraction. I just like to give you as a percent. So what about this one? If it says no more than 2 red marbles, I'd like you to think about what are the options there of what could I set up, and would it be an and or would it be an or when I do that? And we'll talk about that one in class. All right. So that was mutually exclusive events that can't happen at the same time. Well, when you're adding, if you're saying this or that, you have to also think about what happens if they could happen at the same time. So the vocab word there is inclusive. Inclusive means they can happen at the same time. And so to me, that always makes me think of Venn diagrams. So it says the probability of inclusive events, if they can happen at the same time, we're still talking about A or B happening, but now we have to subtract out the chance of them both occurring at the same time. So we're going to say it's a probability of A plus a probability of B minus the chance of both of them happening. And just real quick, I'm going to give you a Venn diagram lesson here, right? Those are some lovely circles. If this was a chance of probability A happening, and this was a chance of probability B happening, if they could happen at the same time, you've counted too much. And so Mr. Price and I have talked about this, and he said he doesn't ever really think of it this way because he just automatically subtracts out the overlap in his head. So he doesn't have to think about subtracting it out because he already thinks about that. I'm the formula girl, and so I like to just do it and then subtract it. But just know we can't count that twice or we've counted too much, and we'll show you an example of that. Okay? You want me to do the first one?
Sure.
The first one's always easier than the second one. So, example 3. This one says we have 2,400 subscribers to an internet server, 1,200 own brand A and 500 own brand B. This is a terrible problem. And 100 own both A and B. Why do you need 2 internet servers? I'll never know. What is the probability that the subscriber will own A or B? So this is set up perfectly to subtract out the overlap, right? So I'm going to take the probability of A plus the probability of B, and I'm going to subtract out the probability of both, okay? So how many own brand A? 1,200 out of 2,400. Something that people always point out to me is that this doesn't add up to 2,400. Well, what does that tell us? It tells us that there's more than just brand A and brand B, because 1,200 own brand A, 500 own brand B, and 100 own both A and B. But there's 2,400 people, which means there's obviously another brand out there, so don't think too much into that. Brand B, 500 out of how many total subscribers? 2,400. But if we count 1,200 for A and 500 for B, we've counted that. We've counted stuff twice, so we have to subtract out the overlap there, which is 100 out of 2,400, which is 1,700 minus 100, which is 1,600 over 2,400, and 16 over 24 is 2/3, which is 66.7% of the subscribers. Okay, so that's very straightforward. Now let's look at one that's not so straightforward. And step 1 is, if you don't know about a deck of cards, we need to talk, because you have to know how many cards are in a deck and the different suits in a deck, and you have to know the different suits. Did I say that already?
Yes.
How many of each suit, and like how there's 4 queens and there's 4 fours and all of that stuff. And so if you don't know that, you might feel a little lost on this, but we can talk about it in class.
So this example is asking what the probability of randomly choosing a queen or a diamond from a standard deck of cards are. Well, we should know that a standard deck of cards has 52 cards. So our denominator is going to be 52. Well, there are 4 queens in a deck. All right. So we know the first probability is 4 out of 52. Or a diamond, so plus, we know that there are 13 diamonds in a deck of cards because there's ace through king that are all diamonds. But there's an overlap here. There is 1 queen of diamonds, so we have to subtract out our overlap, which is 1 out of 52. So if we add all of these up, we would end up getting 10 out of 52. Which is
16 out of 52, right? 4 plus 13.
I subtracted, yeah. I subtracted.
Okay, just making sure.
I subtracted something incorrectly. Yes, this would be 16 out of 52.
Which is about.
Which is 30.76%. So there's basically almost a 31% chance of getting a queen or a diamond out of a standard deck of cards.
That's it.